So I'd like to present some kind of introduction to one of dominating subjects in our group. So I will speak about Sarnak's conjecture. So first of all, let me go very rapidly through some basic things about natural numbers. So first of all, notation. So by R, we will denote the set of real numbers, then C just stands for the set of complex numbers. In number theory, if you think about natural numbers, so the set of natural numbers begins with 1. So 0 is not a natural number. Please keep this in mind. And then among natural numbers, well, a particular role is played by the prime numbers. We'll come back to this shortly. But if you think about natural numbers, so then there are two basic operations you can make on this set. Namely, we can add natural numbers, we can multiply these natural numbers. And notice a difference between these two structures. So if you think about the addition, so it has the natural generator, which is 1. If I want to obtain any number n, so then I just add 1 n times to obtain n. But if you think about the multiplicative structure, so the situation is more complex. Of course, we all know the fundamental theorem of arithmetics, which tells us that each natural number is represented in a unique way as a product of prime numbers. But then you realize that if you want to obtain any natural number as product of prime numbers, so then you see that this structure is infinitely generated. You need infinitely many numbers to represent n as a product of this chosen set. So the set of the prime numbers is the smallest set of generators for the multiplicative structure, but of course you can choose some larger sets. So another option would be just to take, for example, the powers of the primes. So if you want to understand this multiplicative structure of natural numbers, so then, well, in mathematics, it's often through functions on the structure you're interested in. So what kind of functions should we consider when we think about multiplication of numbers? Well, these should be numbers which somehow preserve the structure. So the basic definition for us is the concept of a multiplicative function. So a function is called multiplicative if its value at 1 is equal to 1, but then u at the product of two natural numbers is the product of the values. Umn is equal to um times u of n, but under the additional assumption that these numbers m and n are a coprime. They don't have common, the greatest common divisor is equal to 1. They don't have common factors. So you may wonder why this assumption is natural. Believe me, it is. One might think that maybe the better definition would be to consider completely multiplicative functions. And here in this definition, we just look at the product of two natural numbers, and then we see that this is the product of the values, and this is unconditional, whichever m and n we take. So why these definitions are correct? Well, you can see that, in fact, if you think about completely multiplicative functions, so they are uniquely determined by their values on the primes, right? If I know that my function is completely multiplicative, I take n is represented as the product of primes, and then I just apply the definition or the basic property of being completely multiplicative. If I take a multiplicative function, so then it is uniquely determined by its values at the powers of the primes. Okay, so now if you take powers of two distinct primes, so then these powers are still co-prime, and you can repeatedly apply this definition. You can also see that once you give the values, any values to the primes or to the powers of the primes, so then these formulas which you see here, they define in a unique way a multiplicative function, which is defined, or completely multiplicative function, which is defined on the entire set of M. So speaking about multiplicative functions, it's the same as speaking about the primes. So then you may wonder, okay, so what are the simplest possible multiplicative or completely multiplicative functions which are non-trivial? Of course, if you put on all primes the value equal to 1, so then you will obtain a function which is everywhere equal to 1. Just look at this formula. So this is, we have to do something. We have to do something with the values on the primes. And you will see that on the next slide, there's two classical functions, Mobius and the Liouville function. And you will see that the values on the primes are still constant, but they are equal to -1. So just please, I mean, when the functions will appear on the next screen, so just keep in mind that these are probably the simplest or among the simplest arithmetic functions. So what is the Mobius function? So the definition, when you see it the first time, it looks weird because, well, the Mobius function takes three values, -1, 0, and 1. Of course, by definition, if we think about multiplicative function, at 1, the value is equal to 1. And then there are two cases. So if you take a number n, which is a product of distinct primes, then the only information I would like to remember is that, do I have an even number of the primes or do I have an odd number of the primes? So this is -1 or 1, depending on the parity of the prime factors. But this is if I have a representation of this number in this form. Remember, please keep in mind, so these numbers are called square-free, because otherwise it means that certain prime appears with a power at least 2 in this decomposition into the primes, and then we just put the value 0. Okay, so then there is this simple exercise to show that the Mobius function is multiplicative, but it's obvious that this function is not completely multiplicative because the value at square, so here's a p square, so this is equal to 0, but mu of p is equal to -1. So then, of course, we don't have this equality. So from that point of view, is it multiplicative or completely multiplicative? The next function, which is the Liouville function, looks better because, well, it takes values -1 and 1. And this function looks at, so if you want to see what is the value at the number n, so you look at its decomposition into the primes, and then what you are interested in is the global number of prime factors counted with multiplicity. Okay, so you see this R1 until Rk, and you see that the sum of them, it just expresses the number of prime factors counted with multiplicities. So this Liouville function is a completely multiplicative function. You can see that there is a basic relationship between these two functions. Namely, if you want to get mu from the Liouville function, so you have to multiply mu by mu square. Mu square is, if mu is with values -1, 0, 1, so mu square will be with values 0 and 1, so it has to be a characteristic function, and that's indeed, this is the characteristic function of the set of square-free numbers. In fact, if you go back, to the primary school, and you remember that, well, between numbers you have something like being coprime. You think about prime factors. So then, if you have any function which is somehow related to this multiplicative structure, so the function you will obtain, it will be a multiplicative function. So a classical example is just the Euler totient function, which if you want to compute its value at n, so you look at all numbers which are smaller than n, and you just compute how many of them are relatively prime, are co-prime with n. So this function, of course, I mean, the values are natural and this is unbounded. So I just wrote this here that, so we have these three multiplicative functions. The difference between them is the following. Well, one of the differences between them is the following, that mu and lambda are bounded functions, while the Euler function is not bounded. And this will play a certain role in a while. Okay, so let's go back to prime numbers. So if you look at the sequence of prime numbers, so P1, P2, P3, etc. So let's say in increasing order. So you start writing them. So then you realize that there is no way, I mean, to see, I mean, what is the rule that they appear in the sequence of natural numbers. So you have an impression that this is a kind of randomness, a kind of chaos. So I just wrote here that looking for a formula, even though, you know, people looked for formulas in the past. So looking for a formula producing the primes is like to look for a philosopher's stone in mathematics. Talking about mathematics. Well, so the intuition somehow, which is I think commonly shared nowadays, is that this set of natural this set of prime numbers is thought of as a random set, whatever it means, right? So we think about chaos. But if we agree with such an approach, so then we should see that functions which somehow put across, you know, this multiplicative structure. So in other words, the multiplicative functions, they should capture this randomness. And then we will try to precise, you know, what we mean. So what do we know for sure about the set of prime numbers? So this is the first, I mean, the first statement is just the set of the primes is infinite. So this is the first year students, well, everybody knows proof of this fact. But then one of the greatest achievements of mathematics of 19th century was the proof of prime number theorem. So the idea is, I mean, what is behind prime number theorem is the answer to the following question. So we take all numbers between 1 and capital N, and we would like to see how many of them are primes. And the answer is that we see n divided by log n prime numbers plus an error. So this notation, this little o notation, lambda notation, it means that if you divide by this number, so you have an expression which goes to 0. So this is just a smaller and smaller fraction of the number which we see here. So of course, we deduce from that the density, well, just think intuitively what is the density of a subset of natural numbers. So the density of the set of prime numbers is 0, right? Because if I look at how many prime numbers I have until n, and I divide by n, so then I obtain something which goes to 0, because I will obtain 1 over log n. So this goes to 0. So there are few prime numbers, but on the other hand, there are plenty of them, because log n is growing very slowly compared to n, right? So these are these two things which, well, there is an interplay between these two things. So in particular, if you look for the nth prime numbers, so remember there's P1, P2, P3. So if I look at this number Pn, so where is it? Well, if you make computations using the prime number theorem, so you obtain it should be about of all the n log n. Okay. So if we agree with this intuition that, you know, that multiplicative functions, they describe to us the randomness of the set of the primes, so this should be somehow phrased in the following, I mean, that should resemble behavior of a sample of a random process. So what random process, I mean the most chaotic process, which means independent, identically distributed process. So in this, of course, in our situation, the values are -1, 0, 1. So this is this clear picture, about randomness, it's somehow perturbed by the fact that I have zeros, right? If I at any non-square free number, I see that the value is equal to 0, and I can't help it. I cannot do anything with that. But beside that, because so relatively to this, what in mathematics we say, relatively to this, we should observe this sample of IID process behavior. So this should be expressed by the fact that besides 0, I have -1s and 1s. So I would like to see, so intuitively, I would like to see that the number of +1s and -1s are approximately the same. And this is an old theorem. This is, you see, that just after prime number theorem. So there was this German mathematician. So I wrote here that it is a German mathematician, Edmund Landau, not Lev Landau for physicists. I think that Lev Landau was 3 years old at that time. So in fact, so what Landau proved is that the fact that this limit, that the mean of the Mobius function is equal to 0, it's equivalent to the prime number theorem. So the simple fact that we have cancellations of +1s and -1s is already equivalent to a deep fact, right? And of course, if you look at definitions, you cannot see immediately any connection between these two facts. So that's a deep theorem. So okay, so prime number theorem tells us that we have cancellations of +1s and -1s, but because this fact is expressed by this, so in fact we don't know if this is really the numbers of +1s and -1s are equal or are close to equal, or how close they are to be equal. And then it turns out that if you start to dig a little bit more than that, you require more than just this simple fact. So for example, you see that here, what I wrote, that we look at this sum, but now we try to normalize this by something like square root of n instead of dividing by n. So the square root of n, but it's 1/2 plus epsilon, so it's something which is bigger. So when we divide by this, so it's still we go to 0. I wrote here that this is bounded, but bounded or going to 0, it's the same because epsilon in this formula is any positive number. So okay, so if you require more, that you have a speed of cancellations of that type, so it turns out that we are already in the Riemann hypothesis situation. So this fact is equivalent to Riemann hypothesis. This was remarked by Littlewood also. I didn't put the precise date. I didn't find it, but it's still 100 years ago. So of course, what you see this formula, it's still in the spirit of this IIDs, because you may think about central limit theorem for IIDs. And also, if you want to see from a different angle, maybe, that why this Mobius function is so basic in number theory or in mathematics, is that if you just look at the Riemann zeta function, and to the right of the critical line, the real part of S is equal to 1. So there are no zeros. So you can think about the reciprocal of this function, and you see that it can be represented as a series, so-called Dirichlet series, and instead of 1, which we have in the definition of the Riemann zeta function, we just put the values of the Mobius function. Okay, so you see that somehow, if we insist on the fact that the set of the primes is random, so sooner or later we finish with Riemann hypothesis, and well, there is another way of thinking about randomness of the primes, or randomness of the Mobius function, and this is another famous conjecture. So even though much younger, it's 1965. So this is Chowla's conjecture, which tells us something about autocorrelations of the Mobius function. So formally speaking, so that's exactly this formula. Okay, so we take correlations of length k. So this number a1, ak, you may think that this is 1, 2, till k. So you have different shifts, and they somehow, when you think about this shift, so you just think automatically, okay, I have the additive structure of the natural numbers, but then this function is multiplicative. And then what I see here, it is 0. So this, in fact, Chowla conjecture is somehow trying to capture randomness of the Mobius function, or in terms of independence of the additive structure and the multiplicative structure of the natural numbers. So you may wonder why there are the powers here. So you see this S1, Sk. So these are numbers which are either 1 or 2. But because the values of the Mobius functions are +1, -1, and 0, so in fact, the only thing we care here is that you can put any number, any natural number here as the power, but the only thing which matters is that is it even or odd? If you put everywhere even numbers, so then of course we cannot expect that this value is equal to 0, because if we put even numbers, so then we have sequences of zeros and ones. This -1 effect disappears, and then to expect that this is 0, it's really very risky, because this would mean that we almost always see 0 here, which is not the case, even for k equal to 1, because for k equal to 1 we obtain just the mean of the mu square, and this is 1 over zeta 2, which is 6 over pi squared. So this is the density of the set of square numbers. Okay, so we have this brief introduction to number theory, to analytic number theory, or maybe to multiplicative number theory. But you may wonder what all this has in common with the theory of dynamical systems. So now I spent some minutes on very brief introduction to topological dynamics and ergodic theory. So what do we do in topological dynamics? Well, in topological dynamics, we deal with compact metric spaces, and then we have homeomorphisms. We consider homeomorphisms of these spaces. And formally speaking, as an object, so Xt is a topological dynamical system. So what do we do with that? Well, we look at orbits. Right, so take a point and we look at images and pre-images, if you like. So okay, so we look at orbits and we ask which orbits are dense. Do we have a dense orbit? How many dense orbits we have? We study closure of such orbits. Sometimes we are interested in the orbits of sets. Then of course we have the problem of classification of these objects, etc., etc. And if we think about classification problems, so then often this is through invariance. Right? Like usual way of doing things in mathematics. So one of the most important invariants in this framework is the entropy. I will not give a definition here; it would take too much time. But I will come back to something which, well, to the definition in special cases. So the entropy is a number. It can be infinity, is a positive number or non-negative number. It can be infinity. It can be also 0, and the 0 entropy means that the system is deterministic. Or we may think that determinism is the same as having 0 entropy. And maybe for physicists, maybe I should have added what is written in this footnote here, that we are also interested in observables, and maybe more precisely in continuous observables, which is the continuous observable is just a numerical sequence, so just a sequence of complex numbers, which we obtain by taking a certain continuous function and a certain point, and we look at the values at the consecutive points of the orbit. So that's just a sequence of complex numbers. So that's topological dynamics, so very simple context. So ergodic theory, it's a little bit more complicated thing, because So the basic objects are probability spaces. So that's set and set, sigma algebra of sets which are called measurable sets, and then a probability measure which is defined on sets which we can measure. Okay, so that's a probability space, and then on this space of points, we have a certain automobile. We have a certain map, and then of course this map has to be somehow compatible with the structure which we consider. So it sends measurable sets to measurable sets. Let's say images and pre-images, for not to complicate things. And then we want to see that the evolution. I mean, so in fact we have a system in which we have the evolution, and the evolution is described in discrete time, is described by the action of t. So now when I have this evolution, so I would like to see what is the rule of this evolution. And here in ergodic theory, we say the only rule which we have is that the volume is preserved. So in other words, we take a subset A, and then we iterate this subset. So of course, after a certain time, probably it will be all over the space. But what we know for sure is that perhaps it is all over the space, but the volume of this dispersed set has not changed. Okay, and then so these are measure preserving systems, and then the basic I would say indecomposability property of such system is called ergodicity. So we don't want to see that. So we have a system, but we don't want to see a subsystem of each in a non-trivial way. So in other words, if we have a set which is invariant, okay, so this is, of course, all equalities here are understood almost everywhere, so up to a set of measure 0. So then somehow, if I have such a set, so then the dynamics is, of course, inside this set, and this I would like to see, because then I have maybe a simpler system to study, etc., etc. So I don't want to see it. So in other words, whenever I see this equality, so then the set is trivial in the sense that it has measure 0 or 1. So in other words, maybe this is more from physical point of view, that if we take any measurable observable on that system, which is constant on the orbits, so then it will be globally constant. So it's again, and well, we study different in ergodic theory. We study different mixing properties. I said that the sets are dispersed all over the space, and that there is the measurement of chaos, etc., etc. And there are these classifications problems. So then there's a problem of good invariance, and one of these invariants is the Kolmogorov-Sinai entropy. So again, I'm not giving the definition here, but I will say a few words shortly. Okay, so now it's the most I would say difficult part of this talk, and not this particular talk, but the talk talking about Sarnak's conjecture. Because we need to speak about so-called Furstenberg systems of a sequence. So we will slowly try to see that studying sequences of these arithmetic functions, multiplicative functions, perhaps it has something in common with ergodic theory. Okay, so let's go back to topological dynamics. So in topological dynamics, we consider homeomorphisms of compact metric spaces. So here is a way to obtain plenty of examples of such systems. So suppose that we have a compact subset of the unit disk. So and just it can be finite. In most cases, it will be finite for us. So just think about it that this is an alphabet. So then what we consider is the space of all sequences, two-sided sequences, okay, so it's here. And this is because A is compact, so the product space is still compact. And on that space, we have, however, a natural homeomorphism, namely, so remember that each point in that space, A to the Z, is just a two-sided sequence. So So one way of seeing that I can move it, I can transport it to another sequence, is just shift the sequence by one position to the left, and you obtain a new point, probably new point. So that gives us really a homomorphism of that space. And then if you take any closed subset of this space, which is also S invariant, so then you obtain S, which acts on S, S, which acts on X, because X is assumed to be S invariant. So this gives us the topological dynamical systems, a topological dynamical system. So this is a subshift. If I take X equal to the A to the Z, so then we speak that this is just the full shift over the alphabet A. So if you think about natural subsets, which are S invariant, so again, the simplest situation would be just first take one sequence in that space. Then this sequence, for this sequence, I can take the orbit via the shift. So I take all left shifts and then right shifts. Okay, so I take the orbit, so I obtain a certain set, which is of course invariant. Orbits are invariant, and then I take the closure because S is a homeomorphism. So the closure is still S invariant, and it's closed. So that's a subshift which is determined by U. So of course there is this problem. So here I take integers, right? And as we have seen, arithmetic functions are defined on n only, but this is not a problem. It's just an artificial problem. I can extend any one-sided sequence to a two-sided sequence, for example, by symmetry, and then I can consider the corresponding subshift. So I will not come back to the problem whether sequences are one-sided, two-sided sequences, all sequences are two-sided sequences. So in this, if we agree with that, so then we can speak about the Liouville subshift, or we can speak about the Mobius subshift. So for example, the Liouville subshift was, the Liouville function was defined as -1 to the number of prime factors counted with multiplicities. So it's -1, 1. So then we symmetrize it. And then we take the closure of the orbit of this point, lambda. So we obtain a subshift, which is a subshift over the alphabet -1, 1. The Mobius subshift is defined completely analogously, but the alphabet has changed, and the alphabet is -1, 0, and 1. So the first thing is that, so the first step we do is that given an arithmetic function, we transform it, or we define an object to which this function appears as a point, and this is the subshift generated by that function. So then we need a word how to pass from topological dynamics to ergodic theory. So you remember that in ergodic theory we need measures which are invariant measures. So okay, so we start with a homomorphism, the homomorphism T, which is defined on a compact metric space. On this compact metric space, we consider the space of probabilistic Borel measures. And so this space itself is compact in so-called weak star topology. I will maybe not formally define this topology, but you will see in a while what's going on. So from this X, we create a new compact metric space. And so this is our M of X. And then we can ask, okay, so I have many measures because I can take Dirac measures. For example, I take a point and I just take the Dirac measure corresponding to that point. But of course, if I take the Dirac measure, so I may have a problem with, proving that this measure is something which is interesting for me, because we are interested in measures which are T invariant, right? Because these are objects we need in ergodic theory. So this set of T invariant measures is a closed subset. It has an additional affine function. It has an additional affine structure, and which somehow tells us, okay, so this is a simplex of measures. and then the simplex has some extremal points, and it turns out that this simplex, the extremal points of this simplex are exactly measures which yield ergodicity. So this is, you see that all this language is very natural, and also confirms why ergodicity is the natural concept in ergodic theory. But how to prove that this set is non-empty? Well, so here is a way to see that it's really non-empty. So, and this is through this concept of Dirac measures, or maybe more precisely, so-called empiric measures. So what do? So I take a point x, then I look at its orbit, let's say forward orbit. So I take x, t square x, etc. Let's say until nk. So then I take the piece of this orbit. So this is from 1 to nk, and I want to define a measure on my space. I put the measure in this way that all the points in this piece of orbits they have the same mass. Okay, so that's exactly the measure which is here. So this is the arithmetic, the Cesaro mean of the corresponding Dirac measures. So now, so I have these measures, and they are in this space M of x, but M of x is compact. So I know that I can choose a subsequence that converges. So if I take this empiric measure and I look what's happening if I move this point by t, so you see that, of course, I change. It's not the same measure, right? This empiric measure is, in general, not invariant, but its push forward is almost the same as the starting empiric measure. So you can guess that when I pass to the limit, so in the limit I will obtain an object which must be T invariant. So in other words, we proved that there are always T invariant measures. So once we have topological dynamics, we have also ergodic theory, and probably there are plenty of measures which are T invariant. So then there is this language here that we say that the point x is generic if, when I take all empiric measures associated with this point x, so then it simply converges to one measure. So, so this is in the weak star topology, and you see here, in fact, I wrote what is the definition of weak star topology. If I take any function f, continuous function, so I have to see that the integrals, they converge to the integral of f against the limit measure. But of course, here, because these are empiric measures, so you see that we consider this kind of expressions, very, very numerical. I can compute this integral very easily. So of course, if this convergence takes place along a subsequence, so then x is called quasi-generic, and because of compactness, again, so each point is quasi-generic for a measure. So given a point x, we can wonder how many limits we have. Okay, so here I saw just one limit, but in general, we have many limits. And if we capture all these measures for which x is quasi-generic, so this set of measures is called visible measures, or I should maybe say that these are visible measures from x. Okay, and the next slide is somehow changing our point of view. You know, well, I don't know if this is the same in physics or in computer science, but well, in dynamics, we are used to averaging in the Cesaro sense, so just arithmetic means. But in number theory, they use other way of averaging, or other ways of averaging, and one of the natural ways of averaging is taking logarithmic averages. So here the concept is that, if you remember that, so the empiric measures were defined in the following way, that you took a part of the orbit, and then on this part of the orbit, each point had the same mass. But now I'm going to change this concept, and I'm saying, okay, so I take this piece of the orbit, I take the empiric measure, but I give a weight to points, right? So if we take 1/n, so these are logarithmic weights, and then so we take, okay, so we put the masses like it is here, and then we have to normalize this by using the the corresponding sum of weights. But of course, here, if I put this, or if I put log of capital N K, it's the same, right? Because asymptotically, this sum is the same as log of N. Well, anyway, it's a nice exercise to see that if I now take a convergent subsequence, obtain a measure which is also invariant, then we can speak about the visible measures from the logarithmic point of view. What should be also remembered that if I take this set of visible measures from one point, so there are only two options. So either the situation is relatively simple, I see one measure, so in other words, the point is generic, or if not, then it's just a drastic change, namely, this set has to be uncountable. So in other words, either I see one measure, or I see uncountably many different measures. Okay, so now we come back to our sequences. Okay, so we just think about arithmetic functions, and what do we call a Furstenberg system? Well, a Furstenberg system is the class of measure-theoretic dynamical systems which I can obtain from visible measures at the point U, which is seen as a point in the subshift generated by this point. And of course, logarithmic Furstenberg systems are defined similarly. So anyway, so what we should somehow keep in mind is that given an arithmetic function, we associate to it probably uncountably many measure-theoretic dynamical systems. And okay, I should say, what is the entropy? Well, maybe at the simplest situation where we have a subshift. So we assume additionally that this alphabet is finite, and if you want to see what is the entropy, so we have this. We have a point in our subshift. So this is a two-sided sequence, and suppose that we take a block, so which means a finite sequence of symbols over our alphabet. And then we just look whether this block appears in our infinite sequence X. Okay, so I have a position J, so I see that B0 is Xj, B1 is Xj plus 1, etc., etc. So, okay, then if we see this indeed, then we say that B appears in X. Then if we want to compute something here, so that there is this natural function, to each K, you associate the number of blocks you can see in your subshift. And then, so this is so-called complexity function. And if you have this complexity function, so then you are interested, how many blocks you obtain, when K is going to infinity. And in fact, I'm interested only in the fact whether this is exponential growth or this is sub-exponential growth. So in case, so you see that, so this limit always exists because of some mathematical properties of this function. So this limit always exists. So if this is sub-exponential, so I see that this is 0. If this is exponential, so this is either a number or it is infinity. So okay, so this is just topological entropy of our subshift. If you take a measure, so there is no great change in the definition. It will be almost the same, except for the fact that I have a measure. So I'm interested to capture, that I'm not computing all blocks, but let's say only those blocks which capture 1 minus epsilon of my space. And then you can somehow figure out what the definition is. So these are these Kolmogorov-Sinai entropies of measures, and well, the relationship between topological entropy and measure-theoretic entropy is given by the famous variational principle, which tells us that the topological entropy dominates. So it should be here S, of course. The topological, and it's everywhere, right? S everywhere. The topological entropy dominates measure-theoretic entropies, but on the other hand, if I have so many measures, then in fact I will capture this topological entropy. In fact, because this is a subshift, there will be always a measure which captures this topological entropy. Okay, so now if we keep this mind of, of all these concepts I tried to present before, so then we can come back to the Chawla conjecture. So maybe first I write this Chawla conjecture for the Liouville function. So this function lambda was taking values +1, -1. So we look at the autocorrelations of these functions, that all these autocorrelations are equal to 0. So this turns out to be equivalent. Remember that we wanted to see that somehow we need we see something like a sample of an IID process. So it turns out that in fact Chawla conjecture is precisely equivalent to the fact that lambda is a generic point for the Bernoulli measure in the subshift -1, 1 to the z. So in other words, it's just if I think for the Bernoulli measure, so I mean this is the simplest Bernoulli measure. I mean the symmetric 1/2, 1/2. So in particular, the subshift generated by the Liouville function is just the full shift. So this looks all very, very simple, but please remember that even this fact is open. I mean, it's a very hard and open question in number theory in mathematics. Right? It's still open. But anyway, we see that in fact Chawla conjecture is just ergodic theory. If we come back to, as I previously defined, Chawla conjecture for the Mobius function, so we see this expression. So of course, here there are difficulties because there are these 3 values, -1, 0, 1, and I have to do something with these zeros. So in fact, you have to see that this is also about being a generic point, but for a special measure. So first of all, I have to capture the role of zeros, and to capture the role of zeros is just to look at the characteristic function of the square free numbers, so the mu square. So this is, I think it's for 80 years old. This was a known result that this point is generic for a measure, but this measure has 0 entropy. So nowadays this measure is called the Mirsky measure. So you have that mu square is generic is generic for a measure with 0 entropy, and then somehow if you look at mu square, so it's a sequence of zeros and ones, but when you go back to mu, so over each one you have either +1 or -1. So it turns out that the probability of changing 1 from mu square to +1, -1 for mu is just 1/2, 1/2. So in other words, intuitively, this measure is Bernoulli, but relative to the Mirsky measure. So finally we got to Sarnak's conjecture. So you remember that when I started, I said that, well, we want to, through arithmetic functions or through multiplicative functions, we want to express randomness of the primes or randomness of multiplicative functions. So here is a way which was proposed by Sarnak 11 years ago. So he says, okay, so this function, this mu n, we think that this function is as random as possible. And on the other hand, if it is the case, so it cannot correlate with something which is not random, right? If I take something, so if I take an observable in a system which has 0 entropy, which is deterministic, I cannot see any correlation between them because I believe that mu is very chaotic. Okay, so that's something which is behind, let's say, his idea. Another way of expressing that we deal with functions which are random. So what makes, you see, so what we claim that this limit is equal to 0 for all 0 entropy systems, for all functions, and for all x's. And in fact, this is this last statement which makes Sarnak's conjecture difficult and deep. Otherwise, if we think in terms of classical ergodic theory, so we have an invariant measure somewhere and we want to almost everywhere condition. So then in fact, it automatically becomes true. And it's not difficult because I mean, it's true, and it doesn't see it does not see the entropy, so it's completely useless. Well, anyway, so Sarnak's conjecture, well, it's still open, but let's say that the true reason for Sarnak's conjecture was the true motivation for Sarnak's conjecture was exactly Chawla conjecture, because Sarnak noticed that Chawla conjecture implies Sarnak's conjecture, so somehow he hoped that people will come back to Chawla conjecture. Chawla conjecture was considered, as a problem which maybe was at least on the level of difficulty of Riemann hypothesis. So by formulating this, he somehow forced people, because many people tried to prove Sarnak's conjecture. But even if you look at this implication, so there was no proof in the original article by Sarnak. So the proof was presented by Tao. Then, 3 years later, we gave a pure ergodic theory proof, as you might have expected. But in fact, this proof was already suggested by Sarnak that such a proof should exist. And of course, it would be extremely wonderful to have that these two conjectures are equivalent. So this is open till today, but I will show you some results in a while, which somehow try to clarify what you can expect here. Well, anyway, it's one of open major problems in this theory. So the first 5 years, people, after announcing this conjecture, so there were many papers, people tried to prove Sarnak's conjecture. In fact, they proved Sarnak's conjecture in many classes of zero entropy systems. When we were writing the first survey on that subject, I think that we had on the list more than 100 papers dealing with this problem, and papers, they appeared in the absolutely top level journals like Anna Sumada Invenciones, Duke, and some other. Well, anyway, there was this activity, but of course, how long you can, confirming, a conjecture without really moving forward. But then this 2015, so 6 years ago, there was a breakthrough, and the breakthrough was, let's say on the level of number theory. I will not talking about number theory too much, but just concentrating on Chawla and Sarnak's conjectures. So Tao came, and to formulate Tao's results, I like to first say, okay, so he came and he said, okay, and he asked, okay, what happens with Chawla and Sarnak's conjecture when we change the way of averaging? So instead of traditional averages, Cesaro averages, we consider logarithmic averages. Okay, so then we obtain this logarithmic Chawla and logarithmic Sarnak, and we have the same questions. And then, so the first astonishing result was that he proved that Chawla conjecture holds for k equal to 2. Okay, before this was known for k equal to 1, which is just prime number theorem I mentioned before. But k equal to 2 was considered, inachievable. So he proved it. And then, in fact, then there were some subsequent papers. I think today they published many papers and trying to prove, that this holds for different k's. So let's say so in fact, it turns out that this works for k odd and for many multiplicative functions. Maybe I skipped this for specialists, but the other result was even more amazing, because he proved that logarithmic Chawla conjecture, the logarithmic Sarnak's conjecture, they are equivalent. That's an amazing paper, and then so remembering that, of course, you may wonder, okay, maybe it's just somehow related to the fact. I like, of course, we would be interested to cross out this logarithm, right? And we'd like to see the Chawla conjecture is the same as Sarnak's conjecture. And it's just a way of changing, the way of averaging. So maybe there are some relations between logarithmic way of averaging and Cesaro way of averaging. But even if you take complex, sequences of complex numbers, so you can see that if you have many accumulation points of these two averaging sequences, so the accumulation points, the sets of accumulation points, they can be even disjoint. So in general, there are no relations between logarithmic averages and Cesaro averages, but nevertheless, and despite of that, we prove that Sarnak's conjecture using Tao theorem and some other arguments, we prove that Sarnak's conjecture, however, implies Chawla conjecture, but it is along a subscript. So that's a joint work with Alex Komilko and Dominik Kwietniak. So in other words, we prove that there is a sequence NL such that all these autocorrelations, they vanish. So if you want to phrase this in a different way, so it means that among Furstenberg systems of the Mobius function, we have what we expected. But this is under the assumption that either logarithmic Chawla conjecture or logarithmic Sarnak's conjecture is proved. But we just know that they are equivalent, that these are still open problems. So then I wanted to tell you a few words about a result which is a little bit underestimated. So that's a result by Nikos Frantzikinakis, so 5 years ago. So basically he proved ergodicity implies Chawla. So let's say the precise statement is that if all logarithmic Furstenberg systems of mu are ergodic, then in fact there is only one logarithmic Furstenberg system, and this logarithmic Furstenberg system is just Bernoulli. So that's what we want to see. So in particular, if somehow we prove that mu is a generic point, this we don't know, but if we somehow are able to prove it, and we know that the Furstenberg system which corresponds to this unique Furstenberg system is ergodic, so then in fact it has to be Bernoulli, or relatively Bernoulli over the mean square. So what's one more result? And here is a result proved 4 years ago by Frantzikinakis and Haas, and this is the most famous result. So that's a paper published in Annals. And they proved that indeed Sarnak's conjecture holds, logarithmic Sarnak's conjecture holds for all deterministic systems. But you have to know that if you look at the invariant measures of your system, so you don't have too many measures, in the sense that if you look at extremal points, if you look at the ergodic measures, so we have only countably many ergodic measures. So in particular, they proved that if we have just one measure, one invariant measure, and this is quite common in dynamics, that you have just precisely one invariant measure. So if we have the system of zero entropy, so then the logarithmic Sarnak's conjecture holds. So there are some further reductions of what we can say about logarithmic Chawla conjecture, and to present them, I need two more definitions. So one of them is going in the concept of going back to the entropy. So Sarnak, he required deterministic systems, but being deterministic, it means that, let's say, the growth of different orbits is sub-exponential. But sub-exponential, of course, there are plenty of possibilities. I can be really sub-exponential, but very close to exponential, but I can be polynomial, for example. So let's try to distinguish between these cases. And here's a definition. So let's say on the topological level, so we have a homeomorphism of a compact metric space, and given n, we consider the following metric. So these are well, this is a family of metrics, dynamical metrics. So if I want to see that x and y are close in this dynamical metric, I have to see that when I look at the orbit of x and y, so most of the time they stay close, but not necessarily always, right? Most of the time, it's just expressed by that this by the fact that this expression is smaller than epsilon. Well, anyway, so we say that the system, a dynamical system, has a polynomial mean complexity if there exists a certain constant. So you see that we will be dividing on n to the k. And what we are interested in is that we take this dynamical metric and we try to cover our space by balls of radius epsilon. And we are interested in the minimal number of such balls covering our space. Okay, so that's the concept. I mean, to capture the complexity, and then we want to see that when we divide this by n to the k, but maybe I forgot somewhere about the logarithm, maybe not. So then this is equal to 0. It's just polynomial grows. So there's no logarithm. It's okay. And then for measures, for invariant measures, it will be the same, but up to the fact that we don't want to cover the whole space, but cover the space up to epsilon. Set of measures smaller than epsilon. So the other definition I need is to speak about algebraic systems. So I should say what are Neel manifolds instead of giving precise definition. Let's just consider a very classical example of the classical Heisenberg group. So we look at the group of all upper triangular matrices. So this is a Lie group. This is a nilpotent Lie group. So this here, X, Y, and Z are just real numbers. And I have a natural subgroup here when I take X, Y, and Z. These are integers. So then I can, of course, this gamma 3 is not a normal subgroup, but I can create the quotient, which is our new space, and on this space I can consider. So this quotient space is called a Neel manifold. It's an example of a Neel manifold, and on that Neel manifold, because this quotient is compact. So in fact, if I look at the Haar measure of this group here, which is of course infinite measure. So on the quotient, it becomes a finite measure. So I have a finite measure, so probability measure, if you like, which is Haar measure of that space. And then we can consider rotations on that space. So we fix a certain matrix, and then any of these cosets, you just send to another coset. And this, of course, preserves Haar measure. So in general, we should consider nilpotent groups, and then lattices in such a group, and then we consider the corresponding spaces, quotient spaces, and consider Neel rotations. In fact, it's more complicated. Picture is just the introduction to see the basic objects which we are studying here. Okay. So then we have two theorems. So one, let's say it's a Chinese school. They produce many results of that type, and this one seems to be the best one. Namely, they showed that if a logarithmic Chao-La conjecture is equivalent to the fact that all systems whose invariant measures yield system-whose polynomial complexity, they satisfy the Sarnak's conjecture. Here it should have been, it's not HCH, it's just S, but of course then it is equivalent to logarithmic Chao-La, which is equivalent to logarithmic Sarnak by Tao's result. And more recent result, then you see that this is this year, is that the logarithmic Chao-La conjecture holds if and only if logarithmic Sarnak's conjecture holds for all for all systems whose all ergodic invariant measures are Neel systems, the systems which we have seen before. So it seems that there are some relations between these theorems, because there is this. So this theorem is by Adam Kanigowski, Joanna Kułaga-Przymus, so myself, and Thierry Delary. But if you go back to a year before, 2 years before, so there was a theorem by Kanigowski and his collaborators, then in fact all zero entropy homogeneous systems, homogeneous, I mean that this, if you think about quotients of Lie groups via lattices, so then they all have polynomial mean complexity. But if you realize what is behind this theorem, that you have to consider all systems, and then you have plenty of measures, and then maybe this plenty of measures, they represent different new systems. So then you realize that, well, it seems that there are no relations between these theorems. Okay, so this is I presented to you now what's happening around logarithmic Chawla conjecture or logarithmic Sarnak conjecture, but we would like to finally come back to the original Sarnak's conjecture. Is there any progress in understanding this conjecture? So in other words, you see, Chawla conjecture is something that something is Bernoulli, as there is a system which is Bernoulli. But on the other hand, we can express this in just simple fact that autocorrelations of the Mobius function vanish. So it would be extremely interesting to know how to replace the original Sarnak's conjecture, which means we are orthogonal to all deterministic observables, continuous observables. Can we replace this by an internal property of the function mu? What kind of conditions should be obtained? And then maybe in number theory they will be able to prove it. So it was from the very beginning, it was a kind of speculations that in ergodic theory, if you think about systems which are orthogonal, whatever it means, orthogonal to zero entropy systems. So on one hand side, you have this complete chaos, Bernoulli systems, so independent processes. But in fact, these are not the only systems which are completely different from zero entropy systems. In fact, the larger class is so-called Kolmogorov. So that's the class of systems which satisfies the Kolmogorov property, or sometimes people say that's completely positive entropy. The idea is that a system that has completely positive entropy if it does not have any quotient which has zero entropy, except of course when we glue everything to one point. Okay, so this was 5 years ago. It was formulated as a formal conjecture, and so this is so this conjecture has been written in lecture notes in 2016 by William Veitch, and he said, okay, mu satisfies Sarnak's conjecture if and only if for each Furstenberg system we have the function pi 0. This pi 0 is just function which looks at the value at point y. It looks at the value at the 0 position, so it sees either -1 or 0 or 1, and that this function should be orthogonal to the L2 space of so-called Pinsker factor. So this Pinsker factor is the largest factor which has zero entropy, which has zero, that this object exists, and it can be even described because it's something that you take this pi 0 and then you look at the past. Okay, so I go back and I look at all the variables I can obtain by going to the past, starting from n, and then I take n larger and larger. So in other words, I take the intersection. So that's called the tail sigma algebra of the corresponding process, and this is exactly the Pinsker factor. So in a sense, I can approximate this Pinsker factor. And okay, so what we proved, and that was the aim of this talk, what we proved this year, maybe in 2020, but this year we submit this for publication, we proved that Veitch's conjecture indeed holds. And my last slide is to explain what does it mean. Well, so this theorem tells us the following. So I want to see that the Mobius function, it satisfies Sarnak's conjecture. So take a block C. So that's a block of -1, 0, and 1. Let's say of any length. So then I look at my Mobius function, and I try to find this block appear on the Mobius function. So I find all these places. So these are places N1, N2, etc. So these are places where I see my block C. Then I take a new parameter, which is, let's say, positive M, and I shift this sequence of returns of mu to the block C, right? Because I can see that I can consider these places. I have my block C, then I move my function mu by the shift, and at a certain time I return. So these are consecutive returns to this block. Okay, so now I shift this return point. So now I have this infinite sequence, N1 minus M, N2 minus M, and S minus M, etc. So over them, I see the values of my Mobius function. So it's either 0. If 0, then I don't care. But it's either 1 or minus 1. So what we want to see is that, again, we return to the very beginning. We want to see the cancellations of minus 1s and 1s for all such sets. And this, well, it has to be uniform. I think I stop here. Thank you very much for your attention.
Thank you. So maybe now it's time for questions. Does someone have any question?
I'm not sure how in practice you can measure the volume if you are using the Dirac functions. So I think you've tried to explain that, but I have not captured that really. Because if we have a simple dynamical systems, let's say something like iterative systems, Mandelbrot type, then we just have points. And what do we do? I mean, measure density of the points. This is what when we do practical applications, then we, for example, try to use something like symbolic dynamics, and that is to divide the whole space into some small boxes and count the number of boxes visited by the trajectories. And that I understand how we can do it, and it's similar to how we estimate fractal measures, etc. But if you want to use the Dirac functions, how do you do it in practice? Sorry.
Now, Dirac measures, you want to say, right?
Yes.
Okay. Well, so you see, I cannot answer precisely your question by a physicist. So from mathematical point of view, if you take a measure and you know that this measure is ergodic, you will always obtain this measure as it will be always visible from certain point. So in other words, if the measure is ergodic, I have to obtain it by averaging Dirac measures, along longer and longer pieces of orbits. If the measure is not ergodic, then it's a problem which somehow you asked for, maybe not precisely, but then not every measure has a quasi-generic point. There really can be problems. But because you added that you also are interested in subshifts, in the situation of the subshift, you will always have a quasi-generic point, but sometimes you have to leave the subspace, the word which you consider, and you have to go, the point which will somehow see your measure, it comes from outside.
Mm-hmm.
So these are theorems which somehow come to my mind, just trying to answer quickly.
Yeah. Well, okay. We our modes of thinking are probably quite different, because you think in terms of theorems and proving something, and I think in terms of using it for some, results that we can derive in practice. For example, if we have any kind of a system where we want to measure, well, self-similarity. We want to characterize, let's say, the trajectories. One approach is called the RQA, the recurrence quantitative analysis, and people have found a number of invariants that they can derive just from displaying the trajectories in recurrence plots. And then they have to define this D function as you had it in, I think, slide 26 or something like that. And once you define the D functions, and so you can say, okay, this is your, yes, just there, yes. Then, well, the TIX and TIY are just 2 points on my trajectories, and I want to see whether this is close enough. And if I define a certain similarity measure like that, I can derive many, actually, they have like at least 7 different kinds of invariants that you can derive from these recurrence plots. And it's quite useful for us, actually, to analyze dynamical systems in practice, because then you can try to estimate things like, whether this is approximately deterministic or not, whether the system comes back to the same areas in the space, and whether it stays close to certain points, so there is a certain trapping time or dwell time, and lots of other things which are important for us. Now the question is how this approach, well, as I said, this is a different, definitely, mode of thinking or looking at things, because we would like to derive something about the dynamical systems that characterize them, and not just know that, okay, certain theorems can be proved, which is, well, usually useful for some applications, right? But can you think about using this to derive some relevant information about the behavior of the dynamical system?
Well, I think that, well, I tried to talk about that, in fact, about the same approach, right? Because here, you know, the problem came from number theory, right?
Yes.
And in fact, you see, maybe for a non-specialist, it's not kind of a shock, right? For me, when I understood, you know, what these conjectures are about, it was a kind of a shock, because these conjectures, they say that if you consider multiplicative functions, right? So if you consider the primes, let's say, roughly speaking, so then you obtain a certain bunch of dynamical systems, and they have to, and in fact, these old conjectures, 100 years old conjectures, they tell us that I will not obtain any dynamics, but there is only a restricted, you know, list of possible dynamics. So here it is expressed by the fact I have to have Chawla, but being Chawla, it means I have to be an independent process in a sense, right? Maybe relatively independent, whatever. But they say multiplicativity of your function, right? And if I understood correctly in your language, is that this multiplicative function gives me a dynamical system. But now I would like to say something about this dynamical system. And here they say, well, this system is independent. How can I prove it, right? So the whole bunch of these slides I showed you is the approach is I want to prove that there is only one system, but I cannot prove it, right? I know that I have uncountably many systems, and I want to show that in fact these uncountably many systems, they are all the same one system. So I have to do it through properties of these systems, and then finally end up my discussion. No, there is only one system.
Yeah,
okay?
that's interesting. Yes, I think this relations between the theory of numbers in general and the dynamical systems is very interesting. Actually, in 1986, I was writing a book on the graphical representation of model spaces, which was kind of applied mathematics. I wrote a book for Springer, and I was really amazed reading about the number theory, how many applications it has, and especially that I had some Diophantine equations there. And of course, then you have to look at number theory. That was a very long time ago, of course. I think the major difference between us is that you're trying to characterize things in a global way. And we're interested in systems, for example, that evolve in time. And we want to know how they evolve in different time windows. So the global properties are usually helpful. But what is more interesting for us is actually how this thing is evolving step by step. And whether this evolution at some point is similar to what we had in the past and other things like that, right? So we don't try to characterize the evolution in a global way. Things change very rapidly. For example, we look at the EEG and the signals are fluctuating, changing very rapidly, but there is a certain structure. And if you look too closely, you don't see the structure. If you look, from far distance somehow, you also don't see the structure. There's an intermediate level of let's say, accuracy that you have to use to see that there is certain repetitive structure maybe in the whole dynamics. That's from practical point of view. This is what is more interesting to us than the global properties, of course, which can constrain probably some of this. So I would like to understand how your results can constrain what we observe in complex dynamics like that. Maybe it's possible, maybe it's not. That's an interesting question. Okay. For taking time. I mean, there are better mathematicians now in the audience, I guess, than myself. So.
Okay. So maybe I would have a question here. We have seen this relation between topological entropy and entropy defined by measures. And maybe I missed the definition of this measure-defined entropies. And what is the relation to Shannon entropy to Renyi or Renyi entropies?
No, you didn't miss the definition because there was no definition, right? No precise definition. So let's see. Where was this? I think it was before. Oops. Okay, so your question was, okay, so the topological entropy was defined, but let's say in case of subshifts, but I don't remember where was it. But then I said, okay, so the idea is that, so if you, okay, it's here. So if you have a subshift, so then you look at, so let's say that A is, you have just two symbols, right? Just to simplify the reasoning here. So if you look at the total number of blocks, so you will have 2 to the k, right? Just potential blocks if you have just two symbols only. Otherwise, you have, what you see here. But of course, maybe not all blocks, they really appear in some elements of my subshift. Is this okay?
Yes, okay. It is something like k is like a return, yes?
No. Just k is just the length of the block. Okay, so I take blocks of length 7, and then I want to. So let's say that the alphabet is 0, 1. And then you look at all blocks of length 7. At each position, you put either 0 or 1. So you have 2 to the 7 possibilities, right?
Yes.
And then, but then you have your subshift, right? You have this infinite sequences of 0s and 1s, which are in your world. And then you would like to check, okay, I take a block of length 7, okay, of 0s and 1s, and I check, can I see it in one of the objects of my system? Probably no. So then I just cross out, okay, from the list, and I compute the real number of blocks of length 7 that appear in my system. So this gives me a function. And then, which is called a complexity function. And then I just take, I want to see, okay, so just imagine that all blocks appear. So if all blocks appear, so then the ck of x will be equal to 2 to the k. If I take log, I have k, right? K log 2, and then k cancels out with this k, I obtain log 2. So the entropy of the full shift is log 2. Okay?
Oh, so it is just when we in practice calculate, we assume that, let's say the process is ergodic and we can something say from one realization, and we take long realization, and it is in fact in convergence to Shannon entropy.
It will be, this is okay. That's for us, it's just a theorem, right? Shannon, Macmillan, and Bryman theorem, right? In the ergodic case, exactly.
Yes,
it will be the same idea, right? But formally, I mean, if you have a measure, invariant measure, and you want to compute its entropy, so you repeat the same idea, right? That you look at blocks that appear, but now, then you have a new parameter, let's say a new epsilon arrives, and it says, okay, I'm interested in blocks that capture 1 minus epsilon of my space. Okay, and then it's a new complexity function, right? Which depends on the measure. And then I have to somehow go with epsilon to 0. Well, I didn't write the definition, right? It requires some more effort.
Yeah, yes, but this topological entropy is, via assumption of ergodicity.
No. There is no assumption. In the topology, there is no assumption, right?
Yes, but this is the way we in practice calculate Shannon entropy of process from the one realization. So we take.
And you need I agree. And you need ergodicity, right? Absolutely, right. Correct.
Okay, so this topological entropy is somehow closer to this standard.
Yeah, I mean, but it's an interesting story because let's say Kolmogorov-Sine entropy is in the 50s, but it was in the late 60s where they defined topological entropy. So it took really some time to understand what it should be, right? And the variational principle is even later. Right? But then, of course, this idea of variational principle, it gives you have a dynamical system, topological dynamical system. You look for the measures of maximal entropy, and then you have this concept of topological pressure, etc. So this is very much related to physics. I mean, this kind of thermodynamic. This is called in mathematics. It's called in dynamics. It's called thermodynamic formalism.
Okay, so thank you. Maybe more questions?
Well, these are, of course, very beautiful results. I'm impressed very much.
Thank you.
A question concerning this Sarnak conjecture. Does it hold for, so the conjecture is for this particular Mobius function or for all multiplicative functions?
Very good question, and well, congratulations. You are seeing the first time the Sarnak's conjecture, or you just...
Yes.
Okay, so it's, of course, it's a very natural question, and okay. So how to answer? So first of all, Sarnak's conjecture or Mobius is equivalent to if you replace Mobius by Liouville.
Okay.
Okay, so really there is no difference, but on the level of Chawla, it's not so obvious if these two conjectures are equivalent.
No, but
No, okay, I will
as far as I remember, was completely multiplicative, right?
Say it again.
Liouville function was completely
multiplicative. Right. So it's even better than, well, from a certain point of view, it's even better than. But Sarnak said once that Mobius is given by God. However, Liouville is defined by man, so there are different point of view. But just answering your question, it's not expected to be true for all multiplicative functions, but you are absolutely right that it is expected to be true for many multiplicative functions. But that's the whole theory, the whole theory of distance of multiplicative functions Archimedean characters, Dirichlet characters. So it's very close.
I see.
Everything is, of course, sooner or later it's Riemann hypothesis, right? So these are functions. Not all multiplicative functions. They really capture this multiplicative structure of the primes. Not all of them. Some of them are periodic. There are some functions which are not good. It was thought in 2015 that it is true for so-called aperiodic multiplicative functions. And aperiodic means that, well, we have seen here prime number theorem. So in other words, the expected number of primes in the interval 1n. But then you may ask, what is the expected number of the primes in arithmetic progressions? Okay, so that's what's called Dirichlet theorem. And there is the precise answer to this question. And somehow what we are so if we think about multiplicative functions, so we want to consider those multiplicative functions which capture not only prime number theorem, but also Dirichlet theorem. And these functions are called aperiodic. And it was believed that Chawla conjecture, in fact, Chawla conjecture on that level is true on the level of aperiodic multiplicative functions, but then Tao and not only Tao, but also Maxim Radziwiłł, Polish Canadian star in number theory, and Kaisa Matameki, somehow they disproved this conjecture. So they showed not all aperiodic functions. So still you have to restrict. But very good question.
Okay, thank you.
And once you have mentioned that Mobius and Liouville are bounded multiplicative functions, I think that maybe they are the only two, or maybe a plus function everywhere equals 0. They are maybe the only, yes, bounded.
No, at the very beginning of my talk, I said, no, there is uncountably many. So it's here, it's just the first slide. If you want to define a multiplicative function, so you just choose completely, in a complete random way, the values at the powers of the primes. You can put whatever you want, and you define the function.
I know, but if we assume that they are bounded, like a
Mobius. Okay. But if you assume that, let's say that your values you chose are in the unit circle or the unit disk, so you will never leave it, right? If you take powers, so this will be bounded function. This will be multiplicative bounded function. Okay, so still you have uncountably many of them, and it's really an enormous work. So even I gave here, you see, and then you may think, okay, I gave here as an example this Euler-Totian function, right, which is not bounded. But if you divide phi n over n, so it is still a multiplicative function. But this one will be bounded, right, because it's bounded by 1. So it's very easy to sometimes to transform, a multiplicative function which is unbounded into a bounded function.
But if the values are natural, they are still infinite number of them. Yes.
Okay.
If they take natural values.
Okay. So take the following formula. Okay, I want to define a function. So I fix t, let's say t is a real number, and take the function which to n associates n to the power it. I is just, I squared is equal to -1. Okay, so this is a sequence of functions indexed by t, which is real. So you have uncountably many functions. So
yes,
all these
many, okay.
And you have all these functions are of modulus 1. And they are completely multiplicative. Okay, so you have uncountably many, well, you cannot imagine how many functions you can obtain in this way. It's really something.
Okay, thank you.
It's a universe, right? Okay.
Okay, so if there are any other questions? Are there any other questions? So if there are no more questions, so let us thank the speaker again. And okay, I think that in 1st December we plan on next seminar. So just wait for an invitation. Thank you everyone for your attention, and see you next time.
Thank you.
Thank you.
Thank you, guys.
Thank you.
Bye.
Bye-bye.
Thank you. Bye.
Thank you. Goodbye.